Hey, Vsauce, Mr. Canfield here. No, hey, BC Calculus, it's Mr. Canfield. Today we're going to do curves defined by parametric equations. All right, so this is technically a non-calculus thing, but in order for us to do Chapter 9, which is calculus with parametrics, we need to know what a parametric is. So that's why we're doing this. All right. So you are used to function stuff. You are used to f of x is equal to 3x squared minus 4 plus 4x plus 2, something like this, where y is a function of x. As x changes, y changes. So parametrics, what they are, is instead of being a single function, our x coordinate is going to be controlled. So sometimes they'll have the little t here. In our calculator, that's how we're going to see it. But our x coordinate is going to be controlled by t. So we could say x is equal to t, and then we could say y is equal to like 3t minus 2. Or maybe let's say x is t squared or something like this. Basically what's going on here is instead of having some xy graph where I plug in x, I get out y, I plug in x, I get out y, I plug in x, I get out y. Now what's going to happen is we're going to plug in t and we're going to get out an xy point. So like when time is 0, what's x? 0. What's y? -2. Then when t is 1, what's x? 1. What's y? 3 minus 2 is 1. Then when t is 2, x is 4. And y is 6 minus 2, 4. And what happens is instead of being some function where we wind up drawing it from left to right, we draw something that happens over time, and it could be something like this. It could go all over the place. Behavior tends to get very, very strange. So for example, this one, if I go into y equals, this is in what's called function graphing. If I go to, is it table set? No. Is it, no. I have to remember where it is. Oh yeah, mode. You click mode. See how it says func? We're doing function graphing. If we go to par, that's parametric graphing. Now I have x1 and y1. So I could say x is t squared and y is 3t minus 2. And when I go to the graph of this, sure, this one just looks like a plain old, half of a parabola, but this is where the points are coming from. And so if I go to the table, so that's what's going on here. So t doesn't actually show up on our graph. These points show up, but they show up at these times. So if I did something like this, I think, yeah, no, almost. Would this do it? Oh, whatever, we'll get there. So now that I'm putting it away, I'm thinking of things that work. So anyway, let's see if Stu has anything to add that I didn't talk about. I don't think so. So it really is just a matter of if I have an x function and a y function, I can plug in all these different values, get x values, all these different y values, all these different t values, you get all your x's, plug in the t's, get your y. And it might be easier to, instead of focusing on x comma y at the same time when t is -2, instead just focus on the x equation. So when x is t t squared minus 1. When t is negative 2, that's 4 minus 1, which is 3. Then 1 minus 1, which is 0. Then negative 1. Then 1 minus 1 is 0 again. Then 4 minus 1 is 3. Then 3. And 9 minus 1 is 8. Okay, so this doesn't show anything yet because we need y values for these. So now I'll plug in my t values into my y equation. So that's negative 6 over 2, which is negative 3. Then this is supposed to be negative 1. So negative 3 over 2, then 0, then 3 over 2, then 3, and then 9 over 2. So these are xy points. So when t is negative 2, we're at the point 3, negative 3. So we start there, right? And then 0, negative 3 halves. That's 1.5. Then 0, sorry, then negative 1, 0. Then 0, 3 halves. Then 3, 3. Then 8, 9 halves, which is 4.5. And we started here and we ended up there. So what we do is we trace that line and then we use little arrows to show which way it's going. So if I went to my calculator to do this, be careful. I guess it wouldn't change a whole lot in this one, but let me go. So t min, we want to go from negative 2 to 3. We can even just do a t step of 1, and then it'll just do the exact points that we just did. That was in second table set. No, it wasn't. It was in window. If you've never messed around in the window, I definitely recommend trying it out. Scale is, it's like if I went by 5s, if I hit graph now, you'll see I only have little tick marks every 5. And then is res on here? No, okay. So let me go back to function graphing really quick. Yeah, res, so these can mess with like how detailed the graph is. You don't really need to mess with those, but everything else is pretty self-explanatory. Okay, so back to parametric graphing. Cool, cool, cool. All right. So the other thing that we got to talk about with parametric graphing is going back and forth from rectangular to parametric. Because in case you missed it, this right here, this could be written as some rectangular equation. Sorry, rectangular means like y equals. This could be written as a series of y equals equations. It's the top half of a square root function and the bottom half of a square root function. Or you could say this is x equal to y squared minus 1. There's a lot of things we could do for this. So we got to talk about how to go back and forth. There's actually a way to convert these into, again, what we call rectangular equations, into function notation. So what we do, all right, they're having us use a different one. So let's go to number 3. It says x is equal to t squared plus 3, and y is equal to 2t, right? Well, which one of these is going to be easier to solve for t? That's got a squared in it. That doesn't. This is going to be easier. Divide both sides by 2. T is equal to y over 2, or 1/2 y, right? So then I can just go over here and I can say x is equal to 1/2 y squared plus 3. And now I got x is equal to 1/4 y squared plus 3. Oh, hey, that's a rectangular equation. It'd be a little bit better if it was solved for y. Better as in like we could use our calculator to graph it. But does he make us solve for? All right, let's solve for y then. So we'll subtract the 3 from both sides, right? Well, let me let me reverse the sides real quick. So I put the y squared over here, and I'll put the x over here, and then I'll subtract the 3 from both sides. Multiply both sides by 4, and then take the square root of both sides. So that'll give us y equals plus or minus root 4x minus 3. So that's what our picture looked like if we went in and changed it to function graphing, and we did square root of 4x minus 3 and negative square root of 4x minus 3. Did I do something silly wrong? Oh, no, what did I do wrong? Oh, wait. That's not the one we were looking at. We're looking at a new one now. We're looking at x is t squared plus 3, and y is 2t. So is it that one, or is it... Wait, no, they do look different. Negative 10 to 10. So like, it's like right there. This must mean I did something wrong. What did I do wrong? What did I do wrong? What did I do? Let's see. T squared plus 3 and 2t. Those are right. So divide both sides by 2. Boom, boom. Did x minus 3 times 4. Oh my goodness gracious. If you were yelling at the screen earlier, because that should be minus 12. So when we multiply both sides by 4, the 4 gets distributed. Oh my goodness. All right. So there's my rectangular. There's my parametric. They're the same. You might notice that in the function notation in the rectangular one, it breaks around here, and that's just because it's getting close to 0, and so probably the next value they plugged in, because they plug in a bunch of values and get points and just draw all the points. That's all they're doing on the calculator. So it would actually meet at the middle there. Okay, let's look at 4. 4 says x is equal to 1 over root t plus 4. Y is equal to 1 over t plus 4, and it says t is greater than negative 4. Okay. So the interesting thing is this is a domain restriction here. This is saying we're only looking at t's that are more than negative 4. And the reason why is if t was negative 4, this would be 1 over 0. And if t was anything less than negative 4, like negative 5, this would be 1 over negative numbers, or sorry, 1 over square root of negative numbers, or 1 over imaginary numbers. And we don't deal with imaginaries in this course. So which one of these is going to be easier to solve? I think this one's going to be easier. I can multiply both sides by the t minus, or sorry, by the t plus 4. Divide both sides by the y. I'm going to subtract 4 from both sides. So I can get t is equal to 1 over y minus 4. And then I can go over here and I can say, well, then that means that x is 1 over y minus 4. Oh, plus 4. So then those cancel each other out. So I can say this is 1 over y. And if you're like, ew, well, just, this is nice. Here. Well, we want to solve this we want to get y by itself anyway, right? So we have x is equal to 1 over square root of 1 over y. So I'll cross multiply, get the square root of 1 over y times x is equal to 1. Divide both sides by x. And then square both sides and get 1 over y is equal to 1 over x squared. And then we'll cross multiply and get y is equal to x squared. So secretly, I knew that up here because this is 1 over, well, the square root of 1 over y is 1 over the square root of y, right? Because you can take the square root of each of them individually. This is 1 over root y. 1 over flips it to just the normal. So it's x is equal to root y, and then you square both sides. So y equals x squared is what this is. So that means I should get the standard parabola if I go into my parametric graphing and graph this. And we're going from -4 to, I don't know. What did I do wrong? What the heck? Did I make a silly mistake again? I can't see it. All right, I'm gonna reset the calculator memory really quick. Let's try one more time. 1 over the square root of t plus 4, and then y is 1 over t plus 4. And we'll go from -3. Oh, I guess we shouldn't start at -4. I feel silly. I feel like I'm missing something obvious. So I multiply both sides by t plus 4 and divide it by the y. That's it. I'm gonna go examine Desmos, because you can do this in Desmos too. All right, let's see. Oh, if t is greater than -4, then that means that 1 over y minus 4 is greater than -4. So 1 over y is greater than 0. Does that matter? All right, I'm gonna have to figure this out. I'll come back.